Hey guys, in this lesson we're going to be studying magnetism and electromagnetic induction. Here's your bookwork, copy this down, and follow it with this aim: how do magnets behave around other magnets and metals? And follow it up with these do now questions. Don't write in the answers yet, just the questions. Alright, magnets. So magnets have a lot of stuff in common with electric charges. For instance, they can attract and repel one another from a distance, which makes them field forces. And the strength of that attraction varies with distance, meaning like the farther away the two magnets are, the less force of attraction or repulsion there is. But this is a difference because electric charges don't really have poles. You either are negative or you are positive. A magnet has two poles always, the north and the south. And I'll get into something more later, but the north pole of the magnet is actually the north-seeking pole, meaning it's seeking the north pole of the Earth. But there's some stuff there I have to talk about, and of course the south pole is the south-seeking pole. This is one more interesting thing about magnets, guys, which is that if you have like this larger magnet here and you keep breaking it in half, you could do it a lot of times, theoretically right down to the size of an atom, and which leads to this idea that we think that the atoms themselves are magnets, that they just have all of their electrons spinning synchronously, and that's what's causing the magnetic attractions. But how are magnetic poles similar to and different from electric charges? So this is what I came up with. Similar, I said that they attract, repel from a distance, and that the force varies with distance. And different, I said that the magnets always have two poles. Okay, magnetic fields. I think of magnetic fields very much the same way as I think of electric fields, where they enter and leave from like this same pole every time. They form these curved lines, they never intersect. They can go to infinity or they can just go one to the other. So that's why I think of them so similarly. But I have this question for you. Can a magnetic field strength be measured and detected by a beam of neutrons? So I was just reading up here, and it said that a magnetic field exerts a force on any moving charge, and that's how it can be measured and detected. So in this question, I don't think we could measure or detect a magnetic field strength using neutrons because they're not a moving charge. So in the picture here, we have a classic bar magnet, and these are just iron filings from like scraping iron, and they actually will arrange themselves naturally along the flux lines of the magnetic field. So that's one way to reveal them. And this question: magnetic and electric fields have a lot in common. What is similar and different between magnetic and electric fields? So I just said that one of the differences I could think of between the two is that for an electric field, one of the things that you can see sometimes is like this radial pattern with the field lines tangent to the surface at that point. But you would never see that in a magnetic field diagram because you always have the two poles, so you're always going to get these field lines which are never actually touching, but forming closed loops. And then, of course, what they have in common is that they're both field forces, meaning that they can exert forces over a distance, which is definitely a kind of magic. Alright, so here's the deal about compasses. I have alluded to this earlier in the lesson, but basically, here's the North Pole, where Santa lives. Here's the South Pole, where the penguins are. And what we shouldn't take for granted is that when we have our compasses out, and our compasses have the north end of their magnet pointing towards the North Pole, then what does that really mean about the magnetic field of the Earth itself? So yeah, if the North Pole of a compass is pointing towards the North Pole, then that means that the Earth's North Pole is actually, magnetically speaking, a South Pole. So a lot of people like to imagine that there's like a giant bar magnet buried in the center of the Earth, which creates its magnetic field. This is not true, by the way. It's just a little thing people think about. But they think there's a bar magnet in the center of the Earth, and that the southern end of it is actually at the North Pole. So one of the things you'll hear physicists say is like, geographic North Pole or magnetic North Pole, because those are actually opposite poles. The geographic North Pole is here, but it's our magnetic South Pole. Down here we've got our magnetic North Pole, which geographically speaking is our South Pole. So think about that for a little while. All right, but what we really think is happening is that inside the Earth we have not a bar magnet, but we have this molten core of iron and nickel, and it's the movement of that molten metal which causes the magnetic field. It also explains why the magnetic field shifts a bit, and it's even possible that we're up for a flip sometime in the near future. But these things take place over long time scales, so you wouldn't notice anything. But I just wanted to point out in this last question that at the Earth's surface, the magnetic field is actually not that strong. And the reason for that is because the Earth's molten core is it's like in the center of the Earth, and the Earth is pretty large compared to its core. So it just means that there's actually a lot of distance between the source of the magnetic field and the surface of the Earth itself, and the magnetic field strength diminishes over distance. So that's the reason why the magnetic field is actually pretty weak at the surface. All right, magnetic flux lines. On this page, you're just going to learn some rules. I would start by saying that magnetic flux lines always form closed loops, and they never intersect. That's an important one because with electric fields, they sometimes could go from a source to infinity and did not form a closed loop. But so that's different from magnetic flux lines. But the thing they have in common is that they never intersect. So I would also say, this is going to be sort of new for you guys, the magnetic flux lines always leave the North Pole and they always enter the South Pole. And it's thought that they just continue right through the bar magnet and just keep going just like this over and over again. North to south while outside the magnet, south to north while inside the magnet. Here's another representation. It's if you have two opposite end to end, just again out of north into south, never intersecting. If you have two same sides next to each other, if they're both north, it's always leaving north but never intersecting, so they're going to sort of asymptote with each other and go away. And if it were two southern ones, they remember that the flux lines always enter the south. So here they are, entering from infinity or another magnet, and curving right in there, never intersecting, and entering the south. For a horseshoe magnet, you would see some parallel flux lines, just like you might expect in parallel electric plates. But at the ends, you'll notice significant curving. But again, that's also true with parallel electric plates. And always leaving north and entering south, leaving north, entering south. So if we were to put a compass in a magnetic field, of course its needle is its north needle is going to be pointing the way the northern magnetic field lines are going, which is to say they're going towards the south pole of the magnet. So let's draw that in. Let's make that practical and draw that in around this bar magnet right down here. So we're going to form some closed loops, and the directions of those closed loops are going to be determined by my knowledge of the north and the south pole of the magnet. So those were just some examples of field lines that I would draw in using the rules discussed. Magnetic field strength is determined by how many field lines are passing a point, and you can judge the magnetic field strength really easily from a magnetic flux map because of that reason. All you need to do is look for the area of the highest flux density, and that'll be the strongest part of the field. So the strongest part of the magnetic field is there. Do we think that the magnetic field strength is a vector or scalar quantity? The magnetic field strength is B, and it's representing the flux density. So yeah, vector or scalar. Well, because magnetic fields are associated with direction, meaning like that they'll always leave the north end and enter the south end, then they are considered vectors. And in this diagram, the highest magnetic field strength would be at B, if given the choice between A, B, C, and D. So I'm going to go with B. Okay, so in electromagnetic induction, we are going to be generating a potential difference, which you may remember is the reason why electrons want to flow, or voltage. So we can generate a potential difference in a conductive metal simply by moving it around inside a magnetic field. Basically, the way I think about it is we're just going to take the atoms of the conductive metal and move them up and down and slice the field lines. And if we do that, then it creates that potential difference in the conductor. And the potential difference is what's going to set some electrons in motion, which we would call electricity. So what I'm getting at here is that this is one of the major ways we make electricity, is we just take these conductive metals and slice magnetic field lines. It's not as hard as you would think. And that's the reason why we have so many different ways of getting the energy. We can burn coal under it and boil water and get those field lines sliced. But we boil water with maybe coal, or we could use solar energy in some cases. We can use geothermal energy to boil the water. We can use nuclear energy to boil the water. We just need the heat source, but generally what they're all doing is they're using conductors and they're slicing magnetic field lines and creating that electricity that we need. Alright, so here's my question for you guys. If the conductor is moved parallel to the lines of flux, is a potential difference induced? Why? Is a current induced? Why? So is a potential difference induced? No. You can only induce a potential difference using a conductor if it cuts the field lines, not if it runs parallel to them. But is a current induced? Of course not. Currents are only induced if there is a potential difference. Electromagnetic radiation. We have a really great chart on our reference table for electromagnetic radiation, which you'll see in a second. But it's basically a map that shows in short some of the information contained on this slide about electromagnetic radiation. So a lot of us don't really realize it, but there's this one kind of wave, and it is called a transverse wave, and they have shapes that look like this. And they can actually move through space. They don't even need a medium. They can just move straight through space. And they're all really alike in some ways in that they can move through space like that. They have this kind of shape. And they produce the same kinds of electric fields and the same kinds of magnetic fields as they move. But they just have a variety of different wavelengths and frequencies. And based on those sort of varietal differences in wavelengths and frequencies, what we've got are different kinds of waves, like microwaves, light waves, ultraviolet waves, infrared waves. Those are the ones that we use for heat detecting goggles. But also X-rays and stuff that are super medical. But it's all basically the same kind of radiation, which is electromagnetic radiation. So what causes them and what gives them their properties is that essentially the source of every electromagnetic radiation is a moving charge, and that charge could just be vibrating back and forth, or it could be on a vector, like moving from one place to another. And in either case, it leaves behind an electromagnetic radiation. And the frequency of the wave itself will match the vibration of the charge. So if the charge is vibrating at a certain frequency, that's going to be the frequency of the wave. Every time we use a radio or a TV or a microwave, we're taking advantage of this electromagnetic radiation. I want you guys to really take away from this slide that there is really no difference in the kind of radiation that you have in a light versus that you have in a microwave. It's really all the same stuff with just some little properties that are being tweaked. So I guess don't be so freaked out about the microwave. It's not so bad. Down here, the last thing on this page is it says that the diagram below shows two different types of electromagnetic waves. How do they differ? They have different wavelengths and they have different frequencies. So here is your pair up. I will make copies of this for you so you don't need to copy it down. And here's your summary. I do need you to copy these questions down, including a little diagram for each one of these guys, and we will discuss these in class and answer the questions.